Okay. All right. I'll just take two. Uh, no mistakes this time. Um, Rho is, as we said last time, is given by this quantity, and I can integrate by parts to get this. And since I know that 4 pi rho by Poisson's equation has to equal Ke when it's a self-sustaining wave and there's no other source of charge density, then this is my dispersion relation. And again, I can write this as 1 over omega p squared over omega squared. Well, let me do it this way. F dv omega minus kv. And now, instead of writing that, I want to write df dv and dv. What? No, because now I'm unintegrating by parts. I'm going backwards. So the point is, this is a simple pole.
Right.
You
get the minus and you get a minus.
First of all, now we discussed last time how to take the contour here, and let's just go through it real carefully. We assumed e to the minus I omega t dependence, right?
Where do you assume this?
Where we used it all over the place. We used it when we...
Yeah, but in the integral. You don't have it in the integral, right?
No, I'm not talking about the integral. I'm saying when we derived the expression for epsilon, we had this omega. Where did it come from? It came from this assumption. Now I want this to go to 0 at t equals minus infinity. When t equals minus infinity, I want omega to have a positive imaginary part. Would that do it? Because t is minus infinity, so it's minus times minus I omega. If I multiply I by a positive I get a minus sign, so I get e to the minus infinity, which is what I want. So omega has a positive imaginary part, and that means that this is going under this contour integral is going under the pole. But what it really means is that the pole is slightly above the real axis. Question?
No.
Okay. Yeah.
A little bit of
Now, let's see if this is alternate derivation of the Formelli formula. Is this of any use? I rationalized the denominator. I simplified. So this, so these three lines are just algebra, and I can write this. F now is a general F because I have a simple pole in the denominator. So this part is called the principal value. When you expand this in terms of a real part and an imaginary part, the integral over the real part is called the principal value, and this is the integral over the imaginary part, and it's half a residue. And it's just the value of x, but the point is it's independent of epsilon, as we said yesterday. Now we get to the issue of causality. And this is what you may have been thinking of yesterday. What's the connection between the choice of contour and causality? Consider the response of the plasma to an impulse. The electric field is just a single pulse at t equals 0.
Okay.
Delta function. The Fourier transform of it is just a constant in omega.
Yeah.
And epsilon of t minus 1 is the response of the plasma to this pulse. Now notice epsilon is a function of time here. Previously epsilon was a function of omega, and that was the epsilon corresponding to a particular Fourier component of a pulse. But now we're in real time, and epsilon, and I even wrote it epsilon with a twiddle, so you know it's the Fourier transform of the usual epsilon. And this is the response of the plasma to a pulse. Now the epsilon of t minus 1 has to be 0 by causality when t is less than 0. In other words, before the pulse actually happens, you're not allowed to have any response. Which means the epsilon of t minus 1, when t is negative, has to be 0.
Yeah.
Okay, so now let's look at this 1 is just part of every epsilon omega, and that's not what the part we're interested. So we subtract it, and I guess it's okay to put it inside the integral. It means when omega is equal to 0, it's a delta function. But okay, never mind that. The point is, I want when t is less than 0, I want this to be 0. Okay, so now this is the integral of this integral in the omega plane. When t is negative, here we're letting omega, the imaginary part of omega, go to infinity, right? well, no, the imaginary part is positive, but when t goes to infinity, e to the minus omega t, sorry, when t goes to minus infinity, e to the minus I omega t goes to 0. When I'm in the upper half of the plane.
Yeah. Okay. Don't we in the end take this radius of this to be infinite?
Yeah, we do, but that's.
So I don't need to have a minus infinity in time if my time is.
Well, no, you do, because there are always parts on the contour. No matter, it's only infinite on the real axis, but there are always parts. You're always going to integrate from the axis where
Right.
omega is finite, but it's the t being minus infinity that makes it 0. Now, I'm not sure this is coming out right, but this. Epsilon of omega minus 1 should not have any poles in the upper half plane. And
So fall faster than 1 over omega.
that tells you where the pole has to be for epsilon. Here the integrand is epsilon minus 1, right? That's the thing that's not allowed to have a pole in the upper half of the plane. And that's equivalent. Now epsilon was, remember that epsilon was equal to 1 minus omega p squared over omega squared. If I gave omega what we have to do is find the pole for omega, and I don't see that there's. Well, let's write it this way: epsilon minus 1 epsilon minus 1 is equal to minus this, right? So there's a pole epsilon minus 1 roughly when omega is equal to 0. Now what was I thinking here? So I obviously want to avoid that pole. If I give if I give
You want to avoid it? Okay, don't understand.
I want that pole to go below, to be slightly below.
So then you go give you zero.
What?
Because if you take a contrary and you don't have a pole inside, then the integral will give you zero. Should you
I want it to be zero by causality when t is negative. And when t is negative, the upper contour vanishes. So the upper region is the place where I want there to be no pole in epsilon. It sure looks like there's a pole in epsilon when omega is equal to 0. You're pretending that look, omega 0 is the natural oscillation frequency of the plasma. Omega 0 must be omega 0 must be omega p, right? I'm trying to figure out how this goes. If I go back to a natural oscillator, I had that the amplitude in response to a driving force, a frequency omega, was proportional to polarization is proportional to 1 omega omega squared minus omega naught squared, right? That was the amplitude for a charge on a spring oscillating at omega naught. And so there's a pole at omega equals omega naught. If I give omega naught a small negative imaginary part, then the pole will be when omega has a small negative. The pole in this will be when epsilon has a small imaginary negative part. Okay? So that's what I want to preserve causality. I want the pole in epsilon to occur at a value of omega that's below the real axis. And that's just equivalent to taking this contour and leaving the pole at 0 and just going slightly above the real axis. Let me, this is not the best way to say it. I think the best way to say it is to say, look, I have a pole exactly at omega equals 0. I'm exactly at omega equals 0 is where the pole is, and if I just always allow omega to have a positive imaginary part, I'll be sure to go above the pole. I missed the pole,
and it will be 0.
and therefore this contour where I integrate from omega from minus infinity to plus infinity. Let me put it this way.
There is no pole.
When I do this integral, when I do this integral, I do it along a path, not exactly the real axis, but where omega has a slightly positive imaginary part, which means I'm performing this integral slightly above the real axis for omega. That's another way to ensure that the pole here, which is exactly at the origin, lies below the integral, and then there won't be any poles in this whole region, and I'll get 0. That's just another way of saying what I said yesterday, which is that you want the response to vanish when t is minus infinity. What?
But here it will vanish anyway. You don't have any additional...
It'll vanish when t is negative.
If there is no pole and it's a closed contour, it should be 0. Right?
If there's no pole.
Yes.
If there's no pole. How do you
any contour, you don't have to take it to infinity. That's what I'm saying. If inside you have no poles, it should be 0.
Yeah, but the integral just happens to go from minus infinity to plus infinity. This is the integral that we want to evaluate, and therefore I want to be sure that this contour, the semicircle, vanishes. Because I want this to vanish when t is negative, and it will vanish, as you say. It will always vanish.
Yeah, you can take any function and anything you want and do it just like that, and it will vanish. I know that. But we're talking about an integral that goes from minus infinity to plus infinity. I want this semicircle, the integral over the semicircle, to vanish, and that's guaranteed. That this one is.
All right. Let's remember how contour integrals work. This is what you want to find. You want to find this part. To be used the fact that the contour integral, the entire contour integral is 0 when there's no pole. But that won't help you unless this vanishes by itself. The semicircle alone has to vanish. Otherwise, you won't know that the semicircle didn't exactly cancel the straight part.
Right.
So the way you use this infinite semicircle is to know in advance, without any theorems, that it's 0 by doing it explicitly. And the point is, when t is negative and omega has Certainly when
Yeah, you get exponential decay, and it will be zero.
it's
The modulus is 1 from
Yeah.
e to the power minus I omega t.
certainly for t minus infinity is zero.
Right. Yeah.
I actually want it to be zero for any finite t that's negative,
Yeah. That's
and
what
for
I said.
that I have to make sure that
Zero
that the close to the real axis it's
but it's 0 for any t. If we take the modulus of the entire integrand, then just e to the power minus I omega
the
t.
semicircle.
Yeah, if we take just the modulus of the magnitude.
Because the real part of omega is large.
Yeah,
No. This is e to the minus I omega.
So the modulus is 1. And epsilon.
No. But suppose I'm a very large omega, but I'm slightly above the real axis.
But it doesn't matter. You always have one modulus of e to the power minus I omega t, and epsilon minus 1 is falling faster than 1 over omega. So
Just a second.
and the total path in 2 pi omega.
Oh, yeah, because of the 1 over omega squared in the denominator.
Yes.
Right. Okay. What he said is important. Thank you. The key thing is that epsilon is falling faster than 1 over omega. So even if this length is proportional to omega, we know that when it gets, as omega goes to infinity, the value of this integral is 0.
Yes. Because bounded by the modulus. Integral cannot be more than the integral of modulus.
Yes, times the length.
Yeah, times the
Yeah. So what you're saying is, look, that even at t equals plus, even for positive t, this is 0.
yes.
Okay, he's right. I was wrong. For all values of t, this semicircle is 0. It goes to 0 as its radius goes to infinity. So the value of the straight part, which is what I want to calculate, will be 0 and non-zero depending on whether there's a pole above it or below it. If all the poles are below it, then it will also be 0. And the way I have the poles lie below it is to just assume that each wave has a slight positive imaginary part, so I'm actually doing the integral above the real axis. But the problem is that argument seems to work even for positive t. What do I do when t is positive?
I don't understand as why the
What?
location of pole depends on sign of t.
Me neither. And so I'm confused. So I like my first explanation better. That just you have to get rid of the initial conditions at minus infinity. And I have to read. I have to understand this proof a little bit better. Okay. Anyway, what time is it? Let's go into self-consistent Langmuir waves. This is the equation. What you have to do is solve this, and it's all algebra. From here, you get the epsilon equals 0, which is equal to this quantity. No, this should be omega p squared over omega squared, right? I'm neglecting this, which means the term in the parentheses is just 1. I'm canceling out the k squared, so it should be omega over omega squared here. Anyway, it's just algebra, and when you solve it, you get that omega is roughly equal to omega p, but it has a positive imaginary part, which is it has a positive imaginary part if df naught dv is positive, and if this is negative, it has a negative imaginary part. And that's the point. Usually for a thermal distribution, df dv is negative at any value of v, right? Because in one dimension it's a Boltzmann distribution which decreases with p. Anytime df dv is negative, it has a negative imaginary part, which, by the way, is inconsistent with our assumption. Our assumption is they had a positive imaginary part. And it just means that when it's stable, when you have Landau damping, you have to do it the way Landau did it, with initial conditions, to keep everything completely kosher. But when it has a positive imaginary part, then it's okay. And this is called an unstable distribution. It means that that the distribution was growing. And let's say this is omega over k. It means there were more particles at high velocity than there were at low velocity. Because df dv is positive. And that's what makes it unstable. And it's just like population inversion. If you have more particles in the higher energy state than the low energy state, you get a laser in the case of atomic states, and here you get a growing wave. And that's the most important principle of instability. You have to have more particles in the original state than in the final state. More particles in the higher energy state than in the lower energy state, because it's reversible. A particle that's on this side of the resonance can be accelerated, and a particle that's on this side of the resonance can be decelerated. And the question is, but where there are more particles? End of story. That determines what's called an n equals 0 instability. And n equals 0 just means that it was a simple resonance of the particle's velocity with the wave, so that it always feels an electric field in the same direction. and when n is some number other than 0, there's the term n times cyclotron frequency in the denominator. And that's when the wave is rotating around, and then the particle can resonate with it by just keeping. You can have the resonance even when the electric field is changing at a given point, as long as the particle direction changes exactly at the same rate as the electric field, and that's called the cyclotron resonance. And it just means that the n is equal to 1. I have omega minus kb minus omega cyclotron in the denominator, which is to say that omega minus kb is equal to omega cyclotron. So that in the frame of the wave, in the frame of the particle, the wave is gyrating exactly at the same rate as the particle is. Alright, it's 3, so this class is over. I don't want you to keep putting off doing homework. If you want to get credit for the homework, you should do it. I'm handing it on time. When did I give the homework? Yesterday? About cooling, Armstrong and cooling.
Last week.
So it's due today. All right.